In the last video, we took a look at what happens on the outside, or what the end behavior of a polynomial is. In this one, we're going to look at ones where the equations are a little bit more complicated and there's a lot of stuff that can happen in the middle. So in the middle, there's a few things that you're going to be concerned with. We are first taking a look at this particular function right here, which is x cubed plus 5x squared plus 6. And you see it modeled right here. Now, on this one here, notice that it is an odd function because, well, not function, but the highest exponent is odd. And so as we go from left to right, in the long run, it's going to continue going up. Some little stuff in the middle happens, though. Our end behavior as we go to negative infinity is we go down to negative infinity. And as we go to positive infinity, we're going up. And that happens because there's no negative out front. It's just a positive. But what happens in the middle? In the middle, notice that we have a little hill here and we have a little valley there. The hill has what we call a local maximum. If you look just in this little teeny section right here, there is a maximum. And if we click on that, we can see what the point is. Now that is not, the y-coordinate will be your maximum, and it's a local maximum of 24.519 at the point negative 3.33, where x is negative 3.333, and actually that's probably going to continue on forever and be negative 3 1/3. So there's a local max here. Now we call it a local max because it's just a max in this section. If we were to look at the maximum for the entire graph, that's your absolute max. And if this graph continues on forever, there's no absolute max because it goes up and continues going on to infinity. But we do have a local maximum just in this little area here. Any hill that you see will have a local maximum. Similarly, any valley you have will have a local minimum. The local minimum here is 6 because just in this little teeny area here, the lowest value we have is 6. And notice that I'm taking the y-coordinates for maximums and minimums. So the lowest value would be 6, and it happens at x equals 0. Now, that's not an absolute minimum because notice over here, this graph continues going down forever. So there isn't any absolute maximum or minimum for this particular graph. Now, since we have an odd exponent, that ends up being the case. So we're going to take a look at one with an even exponent. Notice that I have two of them on here that we're not actually seeing that do have even exponents. This odd exponent of a 3 for our highest degree did not have a absolute min or max. But let's take a look at one of these bottom graphs here. I'm going to turn this one off and turn this one on. The highest exponent here is 2. And notice that this one is going up to infinity as your x goes to negative infinity. And it's also going, the y values are going to infinity as your x goes to positive infinity. So we have this spot right down here that is a minimum. For this little section right here, it is a local minimum, but it is also the absolute minimum value for the entire graph. There is no other point lower than this point. So the lowest value for the entire graph, the absolute minimum, is negative 12.25. And that happens at this little spot where we could consider it also a local. But in terms of this graph, because it is the absolute lowest spot, we would say it was a absolute minimum. Let's take a look at the other one where we had a 4 for our highest exponent. So our highest exponent is still even. Notice there's a plus in front of it, so we're still going up to positive infinity on the outside. But in the middle, we have a whole bunch of stuff happening. We have a valley here, and we have another valley here. If those go to the same number, then they're both kind of absolute minimums because those are the lowest points. However, this one here is a local max. In this little area, that is a hill, so it is a maximum. But in terms of the whole graph, it's not an absolute maximum because it's not the highest value you see. So let's click on these and notice that the lowest value right here is negative 2.25. Let's examine this one. It is also negative 2.25. So they both have the same y value, which is the absolute lowest y value. So that would be an absolute min. And the local max, it happens right here at 4. Now, let's put a negative in front and see what happens. Notice that it turns down and it changes shape. It doesn't have all the hills and valleys, but now, as you look at it, it does have an absolute max right here at 4. Sometimes you have lots of hills and valleys when you have higher exponents. Sometimes you don't. Notice that this one here has crosses the x-axis twice, and it has a maximum, an absolute maximum at 4. But it's also, because of the negative I put out front, going downwards. So as you go to negative infinity or positive infinity, where the y values are going to negative. Let's go back to the other one and take a look at it. They both have a highest exponent of 4. But now, notice, we have 2 valleys and 1 hill. Notice that these hills and valleys, there are 3 of them. And if you count up all the hills and valleys, there's 1, 2, 3. Those are turning points where you're changing direction. And the exponent here is 4. That's what will happen. You will have at most 1 less than your highest degree for how many of those you will have. But you saw when I changed it to negative that you could have fewer than that also. Because now we only have 1 of them, but 1 is still lower than 4, or lower than 3. So if you take 1 less than your highest exponent, that's the most hills and valleys you should be searching for. Take a look at where we cross the x-axis. There's 1, 2, 3, 4 spots, and our degree was 4. Let's take a look at another function here. I'm going to go ahead and make a new one. And if I go ahead and click on this, I had a -2, a -1, a 1, and a 2. So in this other one, I'm going to do y x plus 2 equals. And then, oh, notice something. Let me back up. That x plus 2, where is it crossing the x-axis? At x minus 2. If you put a -2 into this expression, doesn't it make it 0? That's an interesting fact. Then let's do x plus 1. Notice that made it cross over here. And if you plug -1 into here, you get 0 again. Then let's do x minus 1. Notice now I have something crossing right here, crossing right here, and crossing right here. And those 3 points are all on that original green graph. I'm going to finally add in an x minus 2. What do you notice about that black graph? Didn't it just land right on top of the green graph? This is another way to write the same exact expression. If we were to multiply all these factors out, we would get the green graph, the green equation. Each of these spots here shows you where, in fact, if you're in factored form like this, each of the factors will show you all of the spots where you cross the x-axis. And notice that all of these cross once, which means that you have you're going through each of those spots as if you were creating a line. If you looked at a little teeny section right here, it would look like a line going through -2. If you looked at a little teeny section here, it would look like a line going through -1, and that's because each of these has a 1 on its parentheses, and there are 4 of them, which means that this is a degree 4. And look at the green one. The green one is a degree 4, and they're landing on top of each other, which means they're the same exact equation. Let's take a look at, I'm going to turn these off. Let's go back to this one. This one in blue is a degree 2. Notice it crosses twice. And notice 1 less than 2 is 1. And we have one valley in this whole graph. That follows the same thing that happened with the 4. Now, I have a x-intercept at 1, 0. I also have one at -6, 0. Let's see if I can make a factored form from those and have it land right on top of that blue one, just like I had the black one land on the green one a minute ago. So we would have x plus 6 as a parenthesis, because when I plug -6 into that, I get 0. And then we would have x minus 1 as the other one, because when I plug this 1 in to this expression, I get 0. Notice that I now have a red graph that just landed on top of my blue graph. So one nice thing about these polynomials is if you know where you're crossing the x-axis, you can actually create a polynomial that goes with it. If I wanted to turn this one over, I could put a negative here. And if I do the same thing and put a negative here, notice that one flips over. But notice this flipped over different than that. You know why? It's because this negative is multiplied by all of this. If I go back here and make that negative go around all of that, now notice that they land on top of each other. So make sure that your expressions are equivalent when you're doing that, but they will flip over if you put a negative in the middle. And notice now, instead of having a minimum, we have a maximum up here. But because in factored form, it's still the same factors, I'm still crossing the same spots on the x-axis. Now, we took a look at these even ones here. Notice I have an odd one that I have not shown you yet. We took a look at this one, and if you take a look at this one, it only crosses the x-axis once here. But it does have 2 turning points. We have 1 hill and 1 valley, so that's 2 turning points, and 2 is 1 less than 3. You will have at most 3 spots where we cross the x-axis. This one here happens to only have 1. Let's take a look at this one though. Notice that's still a degree 3 because our highest exponent is 3, but now we cross at 3 spots like this. We still have 1 less than 3 for how many hills and valleys. We have a local max right there at 0.631. And we have a local min right here at -2.113. So if we wanted to do factored form of this, one nice thing is I can see that I have a -2 here, a -1 there, and a 1 there. This -2 will need an x plus 2 for a factor. This -1 will need an x plus 1 for a factor. And this 1 will be an x minus 1. Let's see if that gives the same equation. We're going to do an x plus 2, an x plus 1, and an x minus 1. And notice it lands right on top of that purple graph. So they are the exact same. Let's take a look at one other thing. So far, our factors have all gone through at, they've all had a single exponent on them, and we've just gone through the x-axis. What happens if I put a square on one of these? So I'm going to go ahead and square that one. Notice now I have two factors here, but I essentially have two factors here also. So this x plus 2 counts as two of them because of the 2 on the top. That's considered a multiplicity of 2. So this is now a fourth degree polynomial because we could write the x plus 2 squared as x plus 2 times x plus 2. And then we also have an x plus 1 and an x minus 1. That's 4 factors. So this is now a fourth degree. Notice we now touch the x-axis at 3 spots. But if you look at it, this spot right here, I'm going to take this one off here. This spot here at -2, it kind of goes down and touches it. It's almost like it's a little parabola right here in this spot right here. So that's called a multiplicity of 2. So because it comes down and it acts like a parabola, and a parabola would have an exponent of 2 on its x. So right here at this spot, this is what we call a double 0. It counts for 2 and it has a multiplicity of 2. So -2 is a 0 because that's where we cross the x-axis and your y is 0. But it has a multiplicity of 2. So that's why its expression here, its factor, has a 2 on it. Notice that the plus 1, which would be where x is -1, and when we cross, still goes straight through and its exponent was 1. And this one here still goes straight through and its exponent was 1. Watch what happens when I make this a square. Notice I still have a parabola shape right here. And now I have a parabola shape right here. I've also added on one more exponent, so we have one more factor. So we have 2 factors here, plus 1 more, plus 2 more, that's 5. I'm now a 5th degree polynomial. And notice that's an odd, and we have a different shape. It's not going the same direction as we go out to a positive and negative infinity on your x's. So this 1 is now a double because it's a little parabola shape. The -1 still goes through, so it's a single. And we also have a double 0 right here at -2 because it's got a little parabola shape.